Welcome back to the deep dive. Today we're really getting into the nuts and bolts of artificial intelligence. We're tackling, I think, one of the biggest questions out there. What's the actual mechanism, the fundamental process that lets a machine truly think or infer or even learn?
Yeah, it's a huge question. And that mechanism, as Gerardo Iovani and Giovanni Iovani define it, is what we're calling computational reasoning. It's really the engine at the heart of AI as we know it today.
Okay, computational reasoning.
Exactly. And our mission for this deep dive is to unpack that. We want to look at its history, where it came from, but also face, that big philosophical roadblock that held things up for a while, and then explore the cutting edge stuff, the solutions AI architects are actually using right now.
I like that mission because, to figure out where AI is heading, we definitely need to understand the starting point. Those early days of formal logic, symbolic systems. How did people even begin to think a machine could think? Like Newell and Simon back in the 50s.
Well, they started with something they call the physical symbol systems hypothesis.
Mm.
It sounds complex, but the core idea was actually pretty straightforward and, well, powerful for its time.
Okay.
The idea was, if you have a system, any system, that can manipulate symbols according to a set of rules, just shuffling tokens around based on instructions, that manipulation itself is basically intelligent action.
Huh. So intelligence wasn't about the brain or biology necessarily. It was about the process, the symbol shuffling.
Precisely. It was about the logic, the manipulation of these abstract tokens.
Right.
And that thinking, well, it directly led to what we call classical AI.
Right, the early stuff.
Yeah. And in classical AI, knowledge wasn't really learned from experience, it was given. Humans explicitly programmed in the facts, the rules, everything needed to perform logical steps, like deduction or classification.
Can you give an example? Like, what did that look like in practice?
Sure. Think about those old expert systems. Maybe one designed for, say, medical diagnosis. You'd feed it symptoms, it would follow this really rigid set of if-then rules programmed into it, and then it would spit out a conclusion, a diagnosis.
Yeah. Okay, I think I remember things like that. Very logical, step by step. It sounds robust in a way.
It was systematic, definitely. But being systematic isn't the same as being smart in the messy real world, is it?
No, not really. So why did that purely symbolic approach eventually, well, hit a wall?
Well, the big problem was that it was static, it was brittle. Our sources, like Vernon and Furlong writing back in 2007, they really point this out. These systems were stuck in their context. Meaning they could solve the exact problem they were built for under ideal conditions. But the moment something unexpected happened, maybe missing information or some uncertainty, which is, constant in the real world.
They just broke.
Pretty much. They couldn't handle it. They had no way to deal with probability or ambiguity. The real world is, well, probabilistic and fuzzy, and classical AI just wasn't built for that kind of adaptation.
Okay, so that lack of adaptability, that brittleness, that leads us right into this really deep philosophical challenge that seems to have haunted AI for ages.
Oh, absolutely. It's the famous symbol grounding problem. Researchers like Vadinsky and also Aid and Guzelder, they really wrestled with this for years.
Symbol grounding. Okay, what's the core question there?
The question is, fundamentally, how do you connect these abstract symbols inside the machine, like, the string of ones and doodles that represents the word DOG, to the actual thing in the real world, the furry creature that barks and wags its tail? How does the symbol get its meaning?
Right, because if the symbol DELD inside the computer only points to other symbols, like animal or bark, but the machine has never, seen a dog or heard a bark?
Exactly. It's just manipulating syntax, following the rules of the game, without any grasp of the semantics, the actual meaning behind the symbols.
So it creates this semantic gap, as you called it.
Yeah.
The logic might be perfect, but there's no real understanding.
Precisely. Zero general understanding. Even Herbert Simon, one of the pioneers, admitted that just having formal representation, just shuffling symbols, wasn't enough. It couldn't achieve that flexible, common-sense, human-like reasoning we just do naturally.
Wow. And it's a huge problem, you said.
It's massive. Because even now, there's no single, universally agreed-upon solution. No magic bullet for truly grounding symbols in reality for a machine. Lots of proposed directions involving perception and analogy, but no final answer.
Okay, so if pure symbols weren't cutting it and this grounding problem was so tough, where did researchers turn next? How did they try to bridge that meaning gap?
Well, the main shift was realizing that abstract symbols alone weren't going to cut it. They needed something more. The solution started moving towards perceptual input, analogical reasoning.
Yeah.
A system that could somehow see or compare things, not just define them with logic.
And that shift, that sounds like it leads us away from pure symbolic AI and more towards hybrid approaches.
That's exactly right. The move was towards hybrid systems. And these are really clever, conceptually. The idea is to merge the strengths of both worlds.
Oh, so.
You take the structured, rule-based reliability of classical AI, the logical part, and you combine it with the adaptability, the pattern recognition, the generalization ability of connectionist systems.
Which we mostly know as neural networks today.
Right, neural networks. So theoretically, you get the structured reasoning and the flexible learning. The best of both.
Okay, that sounds promising on paper. Is there a good example of this kind of hybrid system actually working?
Yeah, Sun's Clarion architecture is often cited as a really interesting case study. It was specifically designed to show how you could get knowledge and representations to partially transfer between the symbolic side, the explicit rules, and the connectionist side, the distributed network.
So information could flow between the two parts.
Exactly. Yeah. And this actually allowed the system to do a kind of internal knowledge creation. It meant the hybrid AI could adapt and learn in ways that neither a purely symbolic nor a purely connectionist system could manage on its own. It was more effective.
But I can imagine trying to bolt together two completely different ways of representing information. I mean, one is like this fuzzy, analog, distributed network, and the other is crisp, discrete, logical symbols. That must be incredibly complicated.
Oh, it is. It's really complex. Vadinsky, one of the researchers we mentioned, points out that this very combination, this integration challenge, is still a major hurdle for achieving, genuine semantics, real meaning.
Okay.
But that complexity, that challenge, also kind of pushed the field further towards the other major pillar of modern computational reasoning, induction.
Right. Let's clarify that difference again. Classical AI was all about deduction, wasn't it? Applying known general rules to specific cases.
Yes, pure deduction, top-down logic.
So what does induction bring to the party? Why is it so important?
Induction is basically the engine driving machine learning as we know it. It's about going the other way, starting from specific examples, from data, from experience, and then inferring general patterns, making predictions, generalizing.
Ah, so it's learning from data.
Exactly. If deduction, the classical way, struggled to adapt to new things, induction is all about adapting. It learns and adjusts based on new experiences. That's why, pretty much all our sources agree. You need both. Combining that deductive structure with inductive learning is absolutely critical for the computational reasoning systems we rely on today.
That makes a lot of sense. Deduction gives structure, induction gives adaptability, but induction, machine learning.
Yeah.
It sounds powerful,
Yeah.
but are there risks, downsides?
Definitely. McClure highlights some key epistemological problems, basically issues around knowledge itself.
Like what?
Well, the big one is explainability. When a machine learns inductively from vast amounts of data, it often becomes incredibly difficult, sometimes impossible, to explain how it reached a particular conclusion or why it made a specific prediction. It becomes a kind of black box.
Right, the black box problem. We hear that a lot.
And there's another risk, too. Overfitting.
Overfitting. What's that exactly? Is it like the machine learns the training data too well?
That's a great way to put it. It learns the specific noise and quirks of the particular data it was trained on, but it learns them so perfectly that it actually loses the ability to generalize to new, slightly different situations in the real world.
So, like memorizing one textbook perfectly, but then failing the exam because the questions are worded differently.
That's a perfect analogy, yeah. It becomes too specialized on the training set and fails when faced with reality.
Okay, let's shift gears a bit. If those early logical, symbolic systems had so many limitations, and even hybrids are complex, why did AI researchers start looking outside computer science altogether? Why look towards biology and specifically neuroscience?
Well, because the brain is, the ultimate proof of concept. It's the existence proof of an intelligent, adaptable learning system. So it makes sense to look at how it works.
Using the brain as a model.
Exactly. Neural networks, the connectionist side of things, are directly inspired by brain structures. Connectionism provides this sort of biological constraint. It gives researchers ideas, a template based on reality, for building intelligent systems that can process information dynamically, like we do.
And this isn't a new idea, is it? This connection goes way back.
Oh, absolutely. You can trace it all the way back to the McCulloch and Pitts model in 1943. That was one of the very first, very simple mathematical models showing how you could connect artificial neurons together to sense patterns and perform basic cognitive tasks. Really foundational work.
Wow, 1943. And from that early concept, it then branched out into modeling more specific brain functions.
It really did. Over the decades, we saw researchers develop specific models inspired by neuroscience for all sorts of things, like dynamics, how systems change over time. Beer did work on that. Navigation Arkin's work is relevant there.
And spatial understanding.
Crucially, yes. The work by O'Keefe and Nadel on spatial representation, how the brain seems to build maps of environments, that was hugely influential. And even things like tracking moving objects in dynamic environments, like Bradenberg's vehicle experiments explored.
Okay, so bringing that biological inspiration right up to modern applications, especially maybe in robotics, our sources mention something called attractor networks. Why are these considered so important or powerful now?
Attractor networks are they're a really neat concept, actually. They represent a plausible way that networks of neurons, real or artificial, could maintain a sense of context over time.
Maintaining context, how does that help?
Well, think about doing any complex task. You need to keep your goal in mind, integrate information over longer periods, right? Attractor networks provide a mechanism for an internal network to sort of settle into a stable state that represents that context or memory and hold on to it, even if the inputs are noisy or changing.
So they help the system stay focused or remember what it's doing over time?
Basically, yes. And that ability to stabilize information and integrate it over time is super important for tackling higher-level cognitive problems, especially things like coordinating complex sequences of motor actions in robotics, where you need that persistent goal representation to guide behavior.
Okay, this is fascinating. Let's try and tie some threads together. We keep coming back to this grounding problem, how symbols get meaning. We know pure symbols struggled. We know connectionist systems draw inspiration from biology. So when we talk about grounding now in this more modern, practical context, what does it actually involve? How do we achieve it, even partially?
Well, Morgan and Bacchini offer a really useful practical definition here. They suggest grounding is essentially about relating the internal structure of the system, its representations, to its function, its meaning, and its reference in a specific context.
Relating internal structure to external context.
Yes, it's about establishing a meaningful link, a defined relationship between what's going on inside the machine and the part of the external world it needs to interact with or understand.
Okay, I think we need a concrete example to really make this click for everyone listening. That example from Morgan about artificial timekeepers sounds perfect for illustrating this practical grounding.
It's a great one. So in this study, they designed an artificial system whose job was to represent circadian cycles, the daily rhythms of light and dark.
Like an internal clock for a machine.
Sort of, yes. But the crucial part wasn't just representing time abstractly. The system was designed so that its internal processes establish what's called a homomorphic relation to the environment's temporal patterns.
Okay, homomorphic relation. That sounds a bit academic. Can we break that down?
Yeah.
What does it mean in simple terms?
Think of it like a structural map or a mirror. The way the system's internal state changed over time, its internal temporal organization, didn't just symbolize the day-night cycle. Its structure directly corresponded to, it mirrored, the actual temporal order of events in the environment, the real cycle of light and darkness. There was a structural similarity.
Got it. So the internal structure matched the external structure it was supposed to represent. And what was the result? What could the system do because of this accurate internal mirror?
Well, because the machine's internal clock was properly grounded, because it accurately corresponded to the real environmental cycles, it could then effectively control complex processes in, say, a simulated plant system.
Like what kind of processes?
Things critical for survival, like regulating photosynthesis, managing water usage, controlling leaf movements, all things that depend on syncing up with the daily light cycle. The machine's grounded internal representation allowed it to perform successful, goal-directed actions in its environment. It shows how having the right kind of internal representation explains how a system can behave effectively.
That's a fantastic example. It really shows grounding not as some abstract philosophical puzzle, but as a practical engineering problem, getting the internal model to correctly map onto the external reality it needs to deal with. Okay, so let's zoom out. We've covered a lot of ground here. We've seen computational reasoning evolve from, well, those very strict 1950s deductive logic systems through that massive decades-long challenge of the symbol grounding problem.
A huge hurdle.
Right up to the kinds of complex hybrid systems we see now, systems that rely heavily on inductive machine learning approaches and often draw inspiration directly from biological brains.
Yeah, the journey has been immense. AI systems have clearly shifted from just focusing on syntax, following the rules for manipulating symbols, towards genuinely striving for semantics, for meaning, by trying to connect their internal workings to an external context.
And it seems like understanding this evolution, studying these different AI architectures and the reasoning techniques they use is becoming incredibly important, not just for building better AI applications, which is obvious, but maybe even for understanding intelligence itself.
I think that's right. It's expected that exploring these computational approaches will not only, lead to amazing new technologies across science and industry, but it could become a primary way for us as humans to develop new kinds of tools and fundamentally get a better handle on what intelligence is.
But as you said earlier, the journey isn't finished. That grounding problem still lingers.
It absolutely does. And that brings us to a final thought, maybe a provocative one for you, the listener, to chew on. If truly human-like understanding, as some argue like AID and Guzelder debated, really requires grounding symbols in the physical external world, perhaps through sensory experience or interaction,
Yeah.
then what does that imply for the future? What fundamentally new physical processes or interactions, things beyond just clever algorithms running on silicon, might we need to introduce into our AI systems to finally truly bridge that persistent semantic gap? What's missing from computation alone?
Wow. That's a deep question. What needs to be added beyond the computation? That really is the challenge, maybe for the next generation of AI research. We'll have to leave it there for today. Until the next deep dive, stay curious.